Yes, please. Welcome back again. Let us look at how we can get the relationship that is linking temperature T and the volume V for a adiabatic process. Now, before we can go ahead and derive this relationship, we need to know what is an adiabatic process. An adiabatic process is a dynamic process where there is no heat is allowed to leave the system of the gas, or no heat is also allowed to enter into the system of the gas. So in this case, an adiabatic process does not allow heat in and no heat out, as simple as that. So if we say for a adiabatic process, we know that du plus dw is equal to 0. This comes from the first law of thermodynamics, which says that the heat that is being supplied goes to do things, increase the internal energy, and then do the external work done. But we are saying the heat that is being supplied is 0 for that case. So let's follow the steps and see how we can obtain the relationship that is linking temperature and volume for an adiabatic process. We know that work done by the gas is given as dW is got by saying P dV, and also we have to know that the work, the internal energy of the gas is given as N C, okay, V change in T. Okay, that is what we have. This is at a constant. We are considering the volume to be constant, not expanding in that case. So we have this process. So let us have that in this case, and for 1 mole of a gas, 1 mole of a gas, we shall have that N is equal to 1. So implying that du becomes CV change in T. That's okay. So we will come here, and then we shall have that du, which is, therefore we'll have that du, which is CV change in T, is equal to, not equal to, sorry, plus dW is P dV is equal to 0. So here for an ideal gas, we know that PV equal to nRT. PV equal to nRT, equation of state, or the ideal gas equation. So I will have that P itself. Therefore, P becomes nRT out of V. So we are going to replace for P back in this equation. So therefore, shall have that CV change in T plus nRT out of V dV would be equal to what? 0 in that case. So you will see that there is dV and then V here, and then there is T here, there is change in T here. So there is a way I need to bring them together. So sorry, I can have this, but let me have this as dt instead. So I'll have this as that. All the same, it's a small change in that. So we can adjust all the same, but I'll just change this one to be a dt for that case here. So I can just have this as dt such that is uniform. So I can have this as dt, of course, like that. So in this case, we can have that CV dt plus nRT times dV out of V will give me what? 0. I can divide all through. Dividing all through by T, dividing all through by t shall have, in this case we shall have CV dt. I'm dividing here by t, all of it would be plus n r. Then I will have dv out of v will be equal to 0, because the t which is here, when divide here by t, it cancels themselves. And if you divide this way by t, it becomes also 0. It remains. Now, but n is 1, sorry, but n is equal to 1. This is 1 what? 1 mole of a gas. We are dealing with only 1 mole of a gas. So that means I'll have CV equal to, no, CV dt over t plus r dv over v equal to 0. But we know the relationship that is linking CV and CP. We derived it. We know that CP minus CV is equal to R, which is the molar gas constant. And I'm going to replace it here for R. So therefore, I will have CV dt over T plus CP minus CV. Okay, we shall have this is dV over V is equal to 0. So from this stage, I am also going to divide, because I want to come out with what we call the principal, the ratio of the principal molar heat capacities, which is Cp over Cv. And the only way I can do that is by dividing all through by Cv. So dividing all through by Cv, like that, dividing all through by Cv, I will have that Cv out of Cv here times dt over T plus Cp over Cv now minus Cv over Cv times dV over V. This is equal to 0. When you divide this way by Cv, it will still give you 0. So I'll have this one cancels, and I'll have the t. I'll have this way. I'll have the t over t plus this one will be Cp over Cv, and then minus 1. This is times dV over V equal to what? 0. But of course, the ratio which is Cp over Cv is equal to gamma, and this one is the ratio of the principal the principal of the ratio of the principal, we call it molar. The principal molar heat capacities, and it varies in the value. It depends on what kind of a gas we are dealing as. Is it a diatomic gas? Is it a monatomic? Is it a polyatomic? All those have different values of Cp over Cv. So therefore, we shall have the T over T plus this one becomes gamma minus 1 now, dV over V equal to 0. So I have replaced for Cp over Cv, which is gamma. So in this case, I can choose now or go ahead and integrate this. So I apply the integral on all the sides of that equation, all through. Apply the integral. So let's wait and see what comes out of it. So on applying the integral, so I'll have that integral of dt over t plus gamma minus 1, I can bring that out, integral of dv over v would be equal to 0. So this is like I am integrating 1 out of t. When I integrate it, I will have a ln of t plus gamma minus 1. And when I integrate this, I will have this is a ln of actually v. And because we don't have the limits being applied, it's like I'm also integrating this way. When I integrate it, I'll get a 0. So this is going to be 0 plus c. And this c is arbitrary constant of integration because we don't have the limits of this integral. So I will have a ln of t plus. This one I can have it as a ln of v, and then I will have gamma minus 1. From the laws of logarithms, this one can come here. So, and therefore this way I will have it as c. So in this case, I can still apply the laws of logarithms here. This is just a natural law. So I'll have a ln of t plus a ln of v, gamma minus 1. So this is actually a ln of t times v, gamma minus 1 as that. Let me put it this way, equal to what? C. So in this case, mathematically, if I want to run away from the logarithmic format to an index format, to the power format, I'll have this one. This is a log to a base of e, a natural logarithm. So this one becomes, this implies that I will have t v gamma minus 1. Okay, this is as a power would be equal to e raised to power c. This is what we get. But this one, e to power c, this is, since this is arbitrary constant of integration, now all of this will become a constant. So in this case, we will have that, therefore, we shall have that t v to power gamma minus 1 is equal to a constant. And that constant is e to power c. And so, therefore, we can write this equation as T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. And you can as well go up to T3. It can be that V3 gamma minus 1, like that. It's equal to a constant. That's the meaning of that. So, this is the relationship that can link. That is linking temperature and volume for an adiabatic process. A process where there is no heat allowed in and no heat is allowed to leave the system. Thank you very much. Thanks for following.